All right, so maybe we should get started. And then, more people will still come. All right, so welcome everyone. So if you're here, hopefully you're here for CS 545, the Introduction to Robotics course. So yeah, welcome to the first day of the class. So this is a course that is like an introduction to robotics. It's mainly aimed at many of the master's students here, but the undergrad and PhDs are also welcome to join. So I hope that this class will be very useful for many people. Now, in terms of some other logistical things, so well, the first thing is we are going to be recording lectures. So I got a bunch of emails about that. So just to make it clear, we are recording lectures. So I have Zoom recording my presentation, and I'll upload the recording on the course website. And the camera is just going to be facing me. So unless you're coming and walking over here, you're not going to be in the camera view. And if you have a question, you can just raise your hand normally and just ask. But if you're a little bit concerned about things like, you don't want your voice in the recording, I have this Google Docs form, and I have my iPad here. So if you want to type in your question, you can just type it in here. You should be able to see it from the Piazza post. So if you just want to type in your question and then just raise your hand, or maybe someone will just tell me, look at this document, then I'll try to answer questions there. But that's if you don't want your voice in the recording. But if you're also sitting far away, then I'm not sure if my laptop can capture your voice anyway. So But yeah, so we're going to be recording everything. So if you do need to miss the class, then you can just catch up there. Then you can just watch it at like 2x speed or whatever. Yeah, and I may try to repeat questions. Like sometimes I have to repeat questions that people ask, and the people who watch the recording won't get it. But I may not always be reliable at that. And yeah, so today's class will be mostly a fun one. It's going to be mostly video, and then some course logistics, and then a few more videos. So we might end a little bit earlier, but most classes will be a little bit more like mathematical or more robotics, technically oriented. Hi. So let's talk about robots. So today, robots are often used in factories. So this is a video that I like to share a lot. It shows the robots that are helping to manufacture cars. And there's this assembly line with partially built cars on it. And each time a new one appears, the robots have a specific task to do. So some of them will just attach the trunk of the car, and then others attach the hood or different parts of it. You can kind of see how it's working there. And this is really nice and effective for something like mass production, where the robots are doing the same thing over and over again, because you could just program the robot, every time this new thing happens, just go to the same picking pose, go to the same placing pose each time. So the robots are very reliable when you ask them to be repetitive, and when they know everything in the environment. Yeah, the robots are very reliable there. But let's talk more about robots that we might want to interact with in our world, in the less structured portion of the world. And this is a video. It's shared from Peter Beal, one of my professors at Berkeley, and I'll just play the video, and it shows this PR1 robot. So that's a really old robot that I don't think people can make anymore, and it shows this robot using different utensils and putting things in the dishwasher and sweeping stuff. So the dream that many robotics researchers, like myself included, have is that it would be nice to have robots that can do stuff like that, and like maybe a home robot that we can ask to do different chores or to help us live our daily lives. But the problem is that, at least the problem with this video, is that everything is teleoperated. So there's a human operator that controlling the robot. And in this case, I think it's a beer can or something, and then the robot is trying to open the cap and then give it to the person. But while this is happening, there's another human that's not shown that is controlling the robot. So the key idea or the key takeaway is that if with the hardware, human can control the robot to do many interesting things, then maybe we just need better algorithms. Because we have the hardware. The hardware we just showed can do this. But we just need a human to help with like helping the robot make the decision autonomously instead of the human teleoperating it. Here's another fun video, also from Peter Beale's group. So show the PR2 robot. So this is the next version of that PR1 robot. And you can kind of see what it's doing. It has a bunch of towels, it's grasping and then scrutinizing it a lot and trying to figure out where to grasp so that you can grasp different corners. And once it looks like it's been sufficiently grasped at two corners, then it can do some hard-coded folding procedure. And then it does the same thing again. So this is a very nice, this was autonomous, by the way. So they developed this algorithm that this robot could use to do this task autonomously. So there's no human teleoperating here. And it's really nice. It's a nice, result on how do you get robots to do these. And of course, I mean, if you look at say like the YouTube video and look at the comments, you see a bunch of people saying, wow, this is very cool, and this is I want robots like this in my home. And you kind of see, what people do, I think. Even for people who are a little more technical, like it's still a nice system result to show robots doing this. Yeah. All right, so here's another video from a different lab at Carnegie Mellon, and which then moved to the University of Washington. Yeah, so they have this robot. It's trying to look at the Oreo cookie. And then they're using this gripper with three fingers and grasping that Oreo cookie. Then I think it tried to separate the two. So one thing that you'll hopefully learn from this class is that fine grain manipulation is very difficult. Robots, they tend to be very good at things like putting together massive car parts, but less good at like fine grain, like knot tying and stuff like that. So, and I think it's scraping away what do you call the inside of an Oreo cookie? I don't know. Filling, maybe. Yeah, cream. There we go. Right, so this is a video from a lab here at USC from Stefanos Nikolaidis. So he actually taught this course last semester. So here's a nice video where they're trying to do robotic line picking. So the objective here is, they have this robot arm, and they're trying to go inside this tree to be able to retrieve some fruit. And from a technical view, one of the interesting novelties here is that they are making contact with parts of the tree that's not the thing that they're grasping. So you'll learn later when we talk about motion planning that when we want robots that execute trajectories in the world, we want them to go to this pose but make no collision with the obstacle. But with leaves, it seems like, it's not a problem if we make contact with the leaf. I mean, it's not like there are like delicate wine glasses that we cannot touch. Uh, yeah, so we'll talk a little bit more about that when we talk about like motion planning and how we get robots to decide, how do we reach some target subject to, different constraints. Uh, Oh, oops. All right, now we have assistive feeding with a robot arm. So assistive feeding is another one of those tasks that we kind of feel like we want. It would be nice to have robots that can do that to help take care of people. And so yeah, in this case, there's some food here. I think it's maybe broccoli, and then you know, giving it to the right pose for the patient to eat. I don't know if it's a patient here or maybe a researcher. Yeah. And of course, when the robot does this, then when we design robots that do this, we have to take into account, not just the kinematics of the robot arm, but the tool that it's holding, or maybe the tool that happens to be attached to it. All right, here's another video. So this is Stefanos. Some of you might know who he is, though he's the professor who taught it last semester. This is Nathaniel, one of his PhD students. And so now they're showing off their really nice system for hair combing. And yeah, you see all these people taking photos, and it looks pretty cool. Then I think they're going to do some hair combing soon. Uh, yeah, there we go. Yep. Now we have a robot that can comb people's hair. And this is in a little more technical detail how the system works. So yeah, there's some camera because you need to see the scene. There's the robot arm. We have them at USC. You might get the opportunity to use them as part of this class. You have to locate the user's hair. Uh, and yeah, and we'll talk a little bit more in the perception part about like things like color and depth and how they're used in robotics. And as with many things in robotics, it helps to test in a simulated environment or something that's like not the real thing before you deploy it. So that's like the test scenario. And it's 20x speed. So just be aware of the speed of the video when you look at a lot of robotics videos, because many academic researchers will speed up the video for obvious reasons. And many robots also move very slowly, also for obvious reasons, to keep things safe. Hi, so there's many more robot systems. So these are just a representative sample of some systems that people have done. So this is a nice system that shows the mobile robot. And the researcher here, Jimmy, was trying to train these robots to push blocks to that receptacle. And one of the things that he did here was he used a technique known as reinforcement learning, which we will talk about later in the class on how do we more efficiently move the item to that receptacle. So instead of doing it one by one, then the more sophisticated version will try to group them together and then use the wall to get more of the blocks there at once. And then that's a little more efficient use of the robot time. Hi, robots that can also toss objects. So this is from Andy Zhang, and he got this robot that could learn to grasp item and then do a tossing motion to get it into that target bin. So I mean, it's cool to look at, but from a more technical view, like it's also interesting to, to see what they did. Like they first developed a tossing trajectory, and then they used machine learning on top of that to learn a lot of the complexity, like, the object can vary a lot, so it mattered where you grasp it, and conditioned on that, then also mattered how fast you try to throw it. And yeah, it's a very nice system. So it helps robots operate outside of their reachable range. And yeah, I mean, if you look, you can look online for the more complete video, but no, the video is really cool. They kept arguing that their system is outperforming the human operators when they're doing the tossing too. So, right. Yeah, so robots can also do things like dynamically manipulate clock. So this is well, it's actually it's a dual arm system. There's a third robot that's just holding the camera. And here they're doing a bunch of picking and placing to try to smooth it, while also doing dynamic motion to spread it out. And the nice thing about this work was it showed basically how do you combine a dynamic motion with what we call a quasi-static motion, which is a very slower, like a slower action that lets the object stabilize before the robot does another action. Let me play the video again. It's a bit short. And then, so yeah, you see the dynamic motion each time they do it. All right, so the robot can also manipulate Rubik's Cube. So I don't know how many of you have seen this before, but it's this work from OpenAI, where at that time they had a robotics team which used the shadow hand to manipulate a Rubik's Cube. You can you can look online for the full uncut video where they showed the full manipulation of a cube. So a couple of things to note here. So no, this was OpenAI back in 2019. So today OpenAI is more famous for ChatGPT and other language model stuff, but back in 2019, they used to have a robotics team, and then they disbanded it, which was probably better for them from a business view, but it also means from an academic view, like, why did they do that? And they did it because robotics is very difficult. This system was trained on a huge amount of simulated data. And then, their paper is titled Solving Rubik's Cube. But if you look at the actual paper, they said something like 20% success rate. I mean, if you have a system that succeeds 20% of the time, then I'm not sure if you call that a solving. Yeah, we have a system that successfully feeds people 20% of the time. We solved it. Anyway, I think it's a good technical result, but it's also it just shows that robotics is very difficult, and we will cover why in many cases throughout the course. All right, so this is one of the works that I was on. So I helped to advise this project. So Lawrence is a PhD student at Berkeley, and he helped to build the system that performs actions on these highly deformable bags. And so the robot is able to do a bunch of primitive action, and then once the bag is sufficiently open, then it can insert the items in there. I'll play it one more time. And again, the video is 20x speed, but a lot of the delay is because we had to take the image and then we had to do a lot of operations on it to like segment it and then decide what to do next, and so on. And this is our follow-up paper, which we presented a few months ago. So here we're trying to separate different layers of the bag. And so the intuition here is when the robot is trying to pull and separate bag, then you can detect whether it got the layer or whether it didn't. In the first case, it didn't. It didn't do it again. But each time that happened, you can only just lower the height when the grip where the gripper goes. So if you just lower it enough, then eventually you'll separate the layers. So then that kind of thing is often the first step in order to do a lot of interesting operation on the bag. All right, so robots can also operate on dough. So this was work that was presented at the conference on robot learning a few months ago. So they're the researchers, they're trying to get this robot to make a dumpling. And it involves things like, you start with a dough, you pick a tool, they use different 3D printed stuff to help them with, so that the robot doesn't actually grip the tool. It just like attaches to it. Yeah. And then once you're at that stage, you'll now flatten the dough, and then they have to try to make it even. I think that's what they do next. Yeah. Yeah. And then they flatten it, and then I think they have to use the tool to make it circular. Yeah. And then they have to brush aside the remaining stuff. And from a technical view, each time the robot is at some stage, there's a classifier that is trained to predict what tool should be used next. And for a condition on a given tool, that they restrict the action space to be specialized to the tool. So it's not like the most flexible action space. Right. And then they show that they make the dumpling. Of course, it has a small amount of filling, so it's not like it has a huge amount of filling inside, but maybe that's future work, they can increase the size of the filling. Yeah. And yeah, I mean, you can look online for the rest of the video, and they also have some nice like robustness results where there's a human operator that tried to destroy part of the dumpling, and then it shows the robot can recover from that and continue. All right, so recently, researchers have also worked on bimanual manipulation from a hardware view. So Tony from Stanford helped to build this bimanual system. It's called the Aloha system. And this is the human that's doing the tele operation. And I guess the point of this video is to show that this hardware is capable of doing many delicate, fine-grained tasks. And if we can do teleoperation, maybe that gives us demonstration data to help train robot to do the similar manipulation tasks. So remember that I mentioned earlier that fine-grained, delicate manipulation is very difficult for robots to do. So I think they're trying to push forward in that direction. And I guess I'll play the whole video because it does look pretty cool. In addition to this, you can look at the website to see the autonomous robot like learning from the demonstration and then deploy to do the task. And this particular thing is not using any tactile feedback, it's just using mainly the visual part. How many of you know what slide I'm going to show next? Yeah. Oh, yeah. I mean, what do you think? This thing? Okay, so a few days ago they announced the mobile version of Aloha. So this is their system now. No, it's mobile now, so it's like a similar set of grippers, and they made it. I mean, they made it mobile, and then I guess the from an algorithmic view, I mean, I have to read the paper to find out a little more, but I think they're using similar techniques on learning from demonstration, just that, the hardware is different. And from what I know, they also made a lot of improvement on since the original Aloha hardware was first presented too. Yeah, then, here they're doing it autonomously. Yeah, so great result from Tony and I think Z Peng as well and Chelsea, their advisor. Yeah, do you have a question back? I mean, is there anything that robots can do that's better than what humans can do?
Yeah.
I mean, well, there are many things that robots can do already today better than humans. It depends on what you mean. So if you're talking about a generalist robot that can manipulate like anything in the kitchen, then I don't think we're at that level. But if you're talking about a single task robot that can manufacture a car, then they're already way better than the human. So it depends on if you're conditioning on, we want the robot doing one task in a very structured environment, then they're way better than human. But if you're asking them to be very generalist and operate in someone's home, then I don't think they're at that level. Like they're not at the human level. So that's my summary. Oh yeah, any other question? And I'm checking the Google Doc as well, where you can type in question, but I don't think anyone had put in question there. So yeah, hopefully that was a lot of interesting video to get you interested in the topic. So yeah, just a couple of administrative things for the class, and then we'll talk a little more about some more videos. So some of the learning objectives for today or for the course are that we would like you to get a lot of proficiency in many of the tools that support state estimation, also for manipulation and for planning. So what we mean by this is that for state estimation, many times the robots have to operate on their assumption of what is their environment. So if the robot is trying to do that like cooking related task that you saw, then the state of the world or the environment is going to be something like maybe it's like the item that it sees in front of it, or maybe the state is interpreted as an image observation and so on. So there's different ways that you can interpret what that means. And often, or basically in any real world robotics deployment, there's always going to be some noise. So when robots have cameras and they look at some scene, there's always going to be like, some noise. Maybe the camera doesn't perceive like the depth values correctly. That often happen when they're at like edges. We'll cover that later in the course. There's also errors in like when the robot does something. So the robot tries to move forward by 3 meters. It might move by 3 meters and 2 millimeters instead of that. So there's always some noise. I mean, sometimes it doesn't matter, but in many cases, you really need to be precise. Like in robot surgery, you need to be like absolutely precise. So we'll cover a lot of like state estimation things, like how do you estimate the state from noisy observations of it. We have a number of algorithms that will teach you, and we're hoping that the homeworks and the lab will give you some experience with implementing those things. And yeah, initially you'll test in simulation, but we hope to have some physical robots that you can test. And I think that's the purpose of the lab that we have. So you'll notice that we have the lecture Monday, Wednesday, and then the labs are on Tuesday. So the lab won't start until later in the course, but hopefully that will, once they do, we can use that time to get you working with some of the physical robots. But yeah, we'll cover more about that later. All right, and some stuff that's a little bit new this year, because this is my first time teaching it. For USC, Stepanov was teaching it the last few years, and then before that, it was Stefan Schkal and Gaurav Sukhotmi, who also taught the course. So my course is going to be, my version will be largely similar, but the main thing that I will try to add are more focused on like machine learning things, more focused on advances in robot perception, as well as language and robots. So I would say that those three areas have gotten super advanced over the last few years. So I mean, you've probably seen a lot of papers or maybe some videos on Twitter or your favorite social media where they show we can command the robot with this image and the text, and then it can do it. So yeah, I'll try to cover a lot of that. That's going to be mostly near the end of the course. So I think the fundamentals will be largely the same. So while it's also nice to be up to date on like some of the more recent advances, there's an argument to be made that it is very important still to know the fundamentals, because when the trends change and different things get hot or not, then hopefully the fundamentals help with getting up to speed on whatever is new or hot these days. All right. Oh yeah. So logistics. So y'all here, you're Mondays and Wednesdays at this time. So if you got here a little bit late, I am recording this lecture. You can probably tell because there's a Zoom stuff near the top. So we'll have the video. I'll post it on the course website as soon as it's ready. And for more information, just look at the course website. So let me just walk through it now. Uh, all right. So this is the course website. Let me just move it up. So you can find it from this website. I mean, you don't have to, you can just look up my name online, then you'll find it. There's the course staff. We do have two TAs. I haven't updated it yet because I only found out who they were this morning. Because things are a little bit chaotic on our end. So if you want to contact us, just use the Piazza. So there's a link here, and I saw some of you have signed up for it. If you haven't signed up, please go there now. Oh yeah, then so if you can use Piazza to contact the course staff, emailing is less ideal. I mean, if it's an emergency or you have a good reason to do so, you can do that, and we'll try to accommodate. But Piazza is the preferred way to contact us. Oh yeah, so when you are posting any code relating or debugging stuff, just make sure that you have read our class policies here about how do you do a proper like debugging or error report. So there's a guide to reporting errors that I wrote. So if you can just take a look at that and just make sure that you read that before you post any like debugging related errors. The reason is that I was previously the TA for a deep learning class at Berkeley. We had coding assignment, and then on Piazza, we had a lot of students say, I had problem with my code, and I tried to help them, but they didn't give me the error message that they got. And they didn't give me the command that they ran. So I couldn't reproduce their steps. So like basically we just, if you have any help, if you need help, we do want to help you, but we just need to be able to reproduce your steps. So yeah, but just take a look at that before you post a debugging or code related question on Piazza. Yeah, any questions so far? So yeah, we have the lecture, the lab, office hours. I'll try to hold them like right after the Monday class. So, I'll be around a little bit today. I can stick around in this room or go back to my normal office, depending on your preferences. Yeah, the course description, you can look at that. Yeah, learning objective, prerequisite. We will cover some introductory topics in probability and linear algebra and calculus in the next two classes. So that will give you a sense of if you have the right background for this. So don't worry, there's a lot of reading material, but you don't have to read the whole thing. Like that's a lot. So each lecture I'll try to cover what I'm actually covering there. So it's going to be a lot more specific than the entire textbook. It's just that I get a lot of information from different sources. So, but yeah, there's like maybe 5 textbooks there. Then there's also a lot of relevant courses. So there's the Introduction to AI and Advanced Robotics from Berkeley. I took the one from Peter Beal, and it helped me a lot in learning about robotics. And I took a look at the Intro to AI course, and it's also very helpful for the foundation. And then these are some previous 545 classes here. And this one has lecture videos as well. Yeah, we'll cover the grading later. And yeah, so this is where I'll have the slide and the recording. And you can see the schedule there. Yeah, question? Oh, all right, so I got a question on the Google Docs. So it said, we're not required to report to class tomorrow since lab will be held sometime later in the course. Yeah, I don't think we have lab. So assume we don't have any lab until we say so. So your Tuesday afternoons and evenings are free up until when we tell you. Yeah. Yeah, and thanks for asking the question. I'll try to keep checking that as well. Okay. Hold on. It should still be fine. All right, so we have Piazza. Just sign up for Piazza and sign up for Gradescope for any grading stuff. Yeah, and then we'll cover more prerequisites later, but just a very quick set of prerequisites. So we will make use of probability a lot. So you should at least be aware of like, what is the PDF of a Gaussian distribution? For linear algebra, you should be comfortable with stuff like, this matrix is positive semi-definite. And for calculus, like if you have a function from Rn to R, like a function from a 3D vector to a scalar, then you should hopefully be comfortable with taking the gradient of that. And with Python, like, can you do stuff like, write vectorized code with NumPy? So yeah, if this whole thing sounds confusing, then talk to me because you might not be in the right class. But if you're familiar roughly with the stuff, then hopefully you'll be fine. Yeah, so the course staff, we will decide on the TA's office hours soon, and we'll tell you that. And yeah, just so I'm saying this again because this is a very big issue that I've run into the past. So I'm hoping we will not have to deal with this. Like we do want to make sure we want to help you. We just need the right information to help you. That's the main thing. Yeah, so in terms of grading, so we will have a set of homework assignments, we will have lab assignments. The difference is that homework assignments will be a little bit more individual, and then there'll be more like shorter with some math questions and then very quick Python programming stuff. The lab will be in groups. Yeah, then we'll have a midterm the week before spring break, and then a final exam. So just make sure that you try submitting all the homeworks and the lab. I mean, you might not, so you might not, get full credit, but we ideally want to see that you at least tried every homework and lab. Yeah, so yeah, homework assignment. So this is the tentative plan, and we will provide the templates to you. So some of you have already seen on Piazza, there's a pinned post and it says link to homework 1, link to homework 2, and I'll be updating that, and then you can just find the homework there. And we'll give you the overleaf template, and then you just type it in your own copy of it, and then just submit that online with to Gradescope. And all right, so another thing that I'm really big on is that like whenever you do an assignment, just make sure that whenever you're like if you're using any external resources, just make sure you cite it, because that's a very important. So we have a question on the homework that says list which resources you have used and consulted. And if you don't answer that, we will have to talk to you about, we'll have to ask you more about that. So like if you're using, like Wikipedia for background material, just say so and say how you use it. So yep, so labs, so we will have groups of roughly 3 or 4 people. So there's one implementation per group. So on Piazza, there's a question, and then once you find your group, just let us know who it is. And just give us all like your GitHub username and so on. And then that way you'll have the same group for the semester. And it will, yeah, so the lab will use what's known as the robot operating system. It's a little bit quirky, but it's also very useful software. It's been used by a lot of robotics researchers today. And yeah, you see here, like this is like a simulation environment where you can simulate the robot. And then that's like the another image of the real robot. All right, so because the labs use ROS, it can be a little bit tricky to get set up. So here's a quick summary. And before we do that, we just want to make sure that, yeah, all the teams should have their own private like GitHub repository. Just don't make it public, and then you'll contact the core staff, and then you'll have your own solution to that. But all right, in order to get set up with it, what I would recommend is trying to get a clean Ubuntu 16 or 20 operating system setup, which depending on what resources you have at your disposal, it can be a little bit complicated to get set up. So we have 2 versions of the lab. So one of them uses Ubuntu 16 and raw kinetic. Unfortunately, uses Python 2, which has been deprecated for quite a while, but no, sorry. And a more recent version uses Ubuntu 20 with raw noetic. But you can do either way. Just let us know which version you're using in your code. And so a couple of ways that you can get set up is that if your laptop already runs the right operating system, then you could just install ROS and see if it works. If your laptop is not like that, like if you're like me and you have like a Mac laptop, then some options are maybe you can do a dual boot, or you can do VMware to get like a virtual Ubuntu setup simultaneously with your normal operating system. So yeah, if you're using VMware, which is what I think most people used in prior edition of the course, then just make sure you start early. Just try to get the whole thing set up and go through all the technical problems early so that you don't run into them later. So like if you're using a Mac, like I am, then this link here will be the one to use. You can just get a free license, and then that will give you VMware Fusion. Oh yeah, then like, I mean, if you're wondering how it looks like, then I can just show you right now. If I can figure out which, yeah. Hmm. Yeah, so the way to use that is that you start up this program, VMware Fusion, and then there's a Ubuntu 64-bit ARM. You just click on that, and then it's kind of like I have Ubuntu 20 here with my normal operating system. So I can click on the terminal. So this is Ubuntu 20. And it basically we will provide you with this, which come with ROS pre-installed. So you can see that you have, you'll figure out, you'll get used to the way that this is structured later, but there's a ROS workspace directory. And then the way that it works is that with ROS, you have this directory, then you install a bunch of packages here. And then for stuff like, lab one, you'll put it in the different directories. And so this is roughly how you can try using it. So we will provide some more detailed instructions on Piazza, so don't worry if this is completely new. Oh, wait. All right, so I see some questions on the Google Doc. All right, so do we have to use ROS with C++ or Python, or is it flexible? So the way, so the assignment themselves, the lab themselves will be using Python, right? But no, ROS can work with either one. So we will have starter code, and then you'll just fill in the Python stuff. TA, do you want to correct me if I'm wrong? Okay, we're good. All right, so if you're using VMware on Mac for ROS, will we need GPU acceleration for training neural networks, such as for assignment 4 with imitation learning? All right, so for the imitation learning homework, I'm going to be using some environments that are really simple. So you should be able to run them with just CPU only. So, and also when people say things like deep imitation learning or whatever, the networks that they use are not actually deep. You might get your input might be 10-dimensional vector, and then you might have 64 neurons in the first layer, 64 in the second one, and then your output. Like that's not deep, but I guess people it's just more marketable to say deep imitation learning. Yeah, so I don't think you have to worry about GPU acceleration. All right, any more questions? All right, so yeah, late assignments. So no, we recognize that many of you might have some conflict that happen. Maybe you're away for something, or something happened. So you'll get 7 late days to use for the whole semester. So for the lab and the homework. So if you're part of a team in the lab, which everyone is, but everyone just keep track of your late days if you're on the same team, so that everyone can pay the same amount if you have to submit it late. And yeah, that's the granularity of a day. So if you're 1 day and 3 hours late, that's 2 days late. But otherwise, if we did fractional day, there would be a lot of administration for us to handle. So. All right, so some policies. So yeah, for labs and homework, then you're welcome to talk about it with some other students in the class. It's just that unless you're part of the same team for the lab, just don't like copy and paste your code or solution. But I mean, if you're on the same team in the lab, then yeah, do whatever you need to do to collaborate. Yeah, I mean, you're welcome to use whatever tool you might want to use. Like if you use Wikipedia, or if you use like a large language model, like a Google Bard, yeah, go ahead and use it. Just use it for like whatever background material you might need, or if you need to use it for something that's not core to the assignment. So if you're implementing an algorithm and we ask you to plot it, then you're welcome to just ask for some plotting code and then just use that. Just make sure that it's not like anything that's like core to the implementation. So we just want to make sure that for the core algorithms, you know how to implement them. Then you'll be tested on them anyway. So yeah, and then yeah, again, we just make sure you cite everything that you use, and we will have a specific section in all the labs and the homework for you to indicate that. Yeah. Yeah, and then yeah, just let us know if you have questions about whatever you like. Generally speaking, my philosophy is like I want you to use whatever is going to maximize your learning. Just tell me what you use. That's the summary. All right, so yeah, the midterm and the final exam, they're going to be roughly similar. So the midterm is before spring break. I mean, if we did it after spring break, I think that would make your spring break not very fun. So we'll do it before. Then the final exam, I believe it's already been scheduled. Like there's a formula for when the exam was scheduled. I believe ours is on May 1st. It's on the website. So just make sure you're available for that time. Yeah. And yeah, you can use your, standard one-page double-sided sheet. You're welcome. You can try to like microfilm the whole slide, but I don't think that's going to be very useful. Like my recommendation is that you start with a blank piece of paper, that you write the core algorithm down, and then different thing that you originally found confusing, but then you just write it there. Because I found that when I was a student, that I actually didn't look at the cheat sheet very much during my exam that I was taking, but the process of making that sheet was actually very useful for studying. But during the actual exam, I usually didn't even look at that because I just knew so much from like actually making it. And yeah, we'll give you more details of that later. All right, any question before we move on to more video? Okay. All right. So, Boston Dynamics. So, I don't know if many of you are familiar with Boston Dynamics. They're like this company in Boston, and they're most well known in the robotics community, I think, for the videos of this humanoid robot that does some kind of acrobatics. So you can kind of see what it's doing. It's doing what do you call them? Somersault? Okay. And they have other things like, backflip and other videos. You can just find it online. And I think the method that they're using is more based on stuff like optimization. Like you try to optimize the pose of a robot subject to some constraint. So I don't think that they actually use a lot of machine learning. But it's kind of hard to tell until we see one of their papers that describes the method. All right, so robots and large language models. So this has been a big theme in robotics the last few years. So this is from Google Robotics. If their say can work, then Brian, the user there, is typing in the input, and that's the input. So the key innovation of say can was trying to combine the language instruction with what can the robot actually do. Like if depending on what it sees, it might not be able to actually do a task that the language model suggests, because the language model just sees text. It might just tell the robot, if it wants to get this Coke can, maybe it should go to a store and buy a Coke. But that's not like what that's not like physically, that might not be physically feasible for the robot. So it was about like merging those language and vision modalities together. And this is also from Google Robotics, it's their Robotics Transformer 2 paper. They based on the name, you can tell there was the Robotics Transformer 1. So this is the second version, that they're more advanced one. And they can do things like, this is the instruction, it has the image from the camera, and it can interpret these commands like move banana to 3. And the key innovation, I guess one of the key, the nice things about this is that it's really one system that can do this. And also this language instruction is a little bit ambiguous. Like, yeah, put the strawberry in the correct bowl. So what is correct here? So it has to do that complex reasoning about which one is supposed to be in or not. And I just barely got it in. Yeah, so move a soccer ball to basketball. And then, yeah, move the Coke can to Taylor Swift. Although I think that's a failure. Move the Red Bull can to H. I got some, there's another question about, will we get sample practice question for the exam? Yeah, I'll try my best to give you practice question. Yeah. So no, when I was a student, I greatly appreciated having the practice opportunity. All right, now where are we? Oh yeah, so yeah, move the banana. What was that? Oh, move banana to the water bottle. There's no banana here. Oh, there's a banana here. Move the banana to Germany. Yeah, so you can see that the system is able to do a lot of this complex reasoning, but there's also like limitations. Like this is not close to like a generalist robot, and it can only do things like picking and placing at very slow speed. And even then, the movement is very jerky because what the model is doing is it's predicting things like the change in the pose of the robot, and it predicts a small change each time step. I then had to re-query the model, so there's always going to be some delay. All right, then this is another exciting work, and which is one that I'm building upon in some ongoing research. So Wenlong was able to get a system that could interpret a language command, and it could interpret like where to grasp, but also which obstacle to avoid based on the language command. And so it combined this language model with the vision language model. And the 3D world, it creates what we call a voxel grid, where each item in the grid is some cost value. So the higher the cost means the robot should not go there. And the lower the cost means the robot can go there. And yeah, these are some of the results. Again, the results have to be tied with a language command. Yeah, and you see that here. And researchers have also gotten together to build a lot of larger data sets for robotics. And this is an example of collaboration. It's called OpenX Embodiment. And you can kind of see the author list. Like whenever you see the author list like that, it's some giant collaboration. So including some people from USC, like I think in Gaurav lab and others. And so what they did was they tried to combine a lot of data from many different robotics labs at different universities like USC and Stanford, NYU, and Berkeley, and so on. And the hope is, you get a lot of data, then the more you have, the more you can use imitation learning to, we'll cover that later in the class, but you can use that to learn the policy. And yeah, you can do stuff like, interpret command like move the apple near the clock versus move the apple on the clock. So there's a big difference between near and on, right? So, and you can see this is also their standard like jerky, robotics transformer, but still a very, very nice result here. And they also visited USC. So last fall, I taught a robotics seminar, and some of the Google researchers, they came and they gave a talk on robotics in the era of foundation models. So foundation models are the big model trained on large data sets that can do many different things. So GPT-4 from OpenAI is an example of a foundation model. And so yeah, some of these researchers, a few of them are actually from USC. So Yevgen, who's over here, he got a PhD at USC a few years ago. So USC is a pretty known contributor to some of the advances in robotics that we're seeing today. Yeah, there's a lot of interest in robotics. If you want to learn more about this particular subject, you can take my class next fall because I am teaching it again. But the rule is for faculty, we can teach a course 2 times, but then we have to change it to a normal course. So then after the second time I teach it, I'll have to change it around a little bit. But the next fall, we will have a lot of discussions about this style of work in a seminar style class. All right, so that's a quick summary. So again, this is a shorter class just for today. We'll have a longer one for the normal classes. And so we're going to release homework 1 later today, the math fundamentals, but you'll have we'll cover the material in the next class and then next week. And yeah, see Piazza for that, and then look at Piazza also for instructions on getting VMware. So the big takeaway is just see if you can get an Ubuntu system set up with ROS. That's basically what you need to do for the first lab. And yeah, tell everyone else to join. And yeah, if you're waiting for declearance or whatever it's called, then hopefully that happens. I don't know what I can do to help with that. And yeah, I don't see any more questions on the Google Doc, so I think we are good for. Wait, no, I think we got all the questions. Yeah. Yeah, so I think we're good for today. Again, I recorded this. I'll post the recording on the website later today or maybe tomorrow morning. And yeah, I'll stick around here if you have any questions. Thanks for attending.